Good afternoon, everyone. Thank you for joining us today. Today is the first day of Earth, Energy, and Environment E3 Conference and Exhibition, second year 2022. My name is Jomana Tariq Abdurazik. I'm a petroleum engineer, a recent master's degree in petroleum engineering graduate from University of Houston, currently working as an engineer in Houston, Texas. I have the pleasure to be here with you this afternoon as a member of the Technical Committee of Earth, Energy, and Environment E3 Conference and Exhibition. Today, we're pleased to welcome our invited speakers, one of which is Dr. Essam Heggy, PhD in space sciences with high honors and a long research experience at University of Southern California. He now works for NASA as a research scientist. Dr. Essam Heggy today will be discussing Earth and environmental sciences in arid areas and the upcoming challenges and the global impact. This session is being recorded and will be uploaded on our YouTube channel, Petro, where you can also find all of our previous and upcoming sessions in Earth, Energy, and Environment Student Conference and Exhibition on our YouTube channel. That's again Petro. Please feel free to send your questions in the chat box and we will answer as many questions as possible. With that, I ask you to give your full attention to our invited speaker and help me in welcoming today's very honorable guest. Please welcome Dr. Essam Heggy. Hi, Dr. Heggy. Thank you for joining us today. We're so glad to have you on Earth, Energy, and Environment Student Conference and Exhibition.
Many thanks, Jomana. Many thanks to everybody for being here. I see we have 120 people right now, so I wasn't expecting such a large number. So today I'm going to talk to you about something that I believe is truly exciting, which is arid areas. So the first time when it comes to you to understand arid areas, you might think only of desert location where there is nothing happening. Today I'm going to take you to two types of arid areas, one on our planet and the other one, which is the largest one, on other planets, and explain how studies of arid areas change our perception of our planet evolution as well as the whole solar system evolution. So I work in two places. The first one is the Jet Propulsion Lab, which is in Pasadena. So JPL was established in 1934, 25 years before the creation of NASA, and then it joined NASA in 1959. JPL by size is one of the smallest NASA center, and by mission, it does about half to a third of the NASA mission. The second place is the University of Southern California. So something so special, which is about 18 miles to the south of JPL. So USC is very known as a school of engineering to be the home of Neil Armstrong. So Neil Armstrong, when he walked on the moon, he was a master student of the University of Southern California. So many people, they know that the first astronaut was a U.S. citizen, but very few people know that Neil Armstrong, when he walked on the moon, he was a student. And that is the master students, and that's a big message for the young students who follow us today, that the first man on the moon was a student, just maybe like many of those who are listening to this talk. So we're going to talk about water, and water in deserts, and water on planets. So the first thing I want to tell you that water is in liquid phase on our planet Earth, but it's in an ice phase and potentially on liquid phase on many other places in our solar system. So a big question that comes all the time, why we have so much environmental, climatic problems on Earth? Why are we spending so much money on looking to Mars? Why we go to Venus? Why we go to the moon? Why we go to the icy moon of Jupiter? Why we go to comets and asteroids? And I'm going to tell you that the first and the main reason why we go to these planets is that each one of them tell us something about our own planet. So for instance, just to make it very simple, we can't go in the past and understand our planet. We can't go in the future and understand how it look like. But for instance, if you look to Mars, which is a desert, Mars is the future of our planet. Venus is the past of our planet during the volcanic age. The icy moon of Jupiter represents the Earth during the ice age. The comets and asteroids, they brought volatiles, water on Earth. Asteroids changed the path of the evolution of our own planets. So each of these bodies represent a phase that our planet has went through. Now, one of the big questions, of course, and we are just a few days ahead from the starting of the conference of climate change is how climate change impacts our own planet. Sometimes the perception of climate change is just limited to understanding the melting of the ice pole on Earth, North Pole, the South Pole, and we tend to believe that climate change in arid areas like the Sahara, Arabian Peninsula, even the southwest of the United States does not exist or has weak impact simply because we have this visual perception that in deserts, nothing happens. It's a desert. So what's going to be? And so then the aim of my talk is to show you that desert does respond to climate change different than icy regions, but they are the testimony of severe climatic fluctuations on our planet. So let's look, for instance, to this part. This is an area that is in the south of Egypt and the north of Sudan. It's an area very dry. And you look to the satellite image that is 100 kilometers by 60 kilometers, and you don't see any evidence of vegetation, of water, of anything. Now, if we use the radar images that we developed to look few meters below the surface, and now you see this is the radar image, this is the optical image, and few meters below the surface, you see these drainage networks, these large drainage networks that witness that this desert about 20 million years ago to 20,000 years ago witnessed a very wet period. So this is telling us that the deserts we know today, a couple of million years ago, they were not dry, and so they were wet and they were green areas. And today, the story of the desert climate change is not on the surface; it is down beneath the subsurface. And when you go to these areas and you stand on the surface of this point here, it's really flat. It doesn't have any testimony of this huge amount of water that were flowing one day at the surface. So then comes the big question, why you are having somebody who work on Mars exploration telling you about Earth climatic and environmental changes? And I'm going to tell you the answer in this question in this very nice table that summarizes the number of publication on groundwater, for instance, in the last 20 years. For Egypt, there was 615 paper we got from Scopus. Saudi Arabia, 535, Tunisia, 406. And this is the deficit in water budget in these nations. And this is the number of the research institute working on water and groundwater in these places. And you can see that on the bottom of this list, planet Mars will top the number of publications on groundwater research in arid areas. It has 0% deficit, doesn't have any deficit. And there are 60 institutes working on groundwater on Mars, which is basically higher than the sum of all institutions working on groundwater in desert regions. So why this? And why finding water on Mars is a fantastic thing that excites everybody, and finding water in our deserts does not passionate the same number of people. And their answer to that is very simple, that the groundwater on Mars is a nice scientific and technological endeavor, while finding groundwater in desert region, unfortunately, is a development and charity programs. This is why it's not inspiring so much young people. Okay? So now, why Mars tell us a lot about our own hazard? So Mars is a sister planet of the Earth. It's about half of the size of the Earth. It's covered with hazards. It have the dust storms, very similar to the Sahara. Very similar to our planet, it has an ice cap in the north and in the south. And very similar to the Sahara, the image I showed you, Mars have fluvial drainage that we see at the surface, which are showing that there is recent water flows that happen, transient water flows that happen on Mars. So these occur at specific moments of the year, and they last for a couple of hours, potentially, before they disappear. So Finding water on Mars is basically answering the question, was Mars a blue planet? And if Mars was a blue planet, is our sister planet. If we understand how water disappeared on Mars, we can understand how water will disappear on Earth. And then we can understand the future of climatic changes on our own planet Earth. So I work on 3 missions that aim to explore this groundwater on Mars. The MARSIS instrument, which 3 of them are sounding radar. MARSIS on board of Mars Express has been launched in 2004. Sharad has been on board Mars Reconnaissance Orbiter, was launched in 2005. And the Wisdom instrument on board ExoMars, which will be launched next year on the ESA rover. And both the 3 of these radar, they aim to look to different depths on Mars, basically from few 100 meters to few kilometers to few meters of the rover. And the big question is, if we find groundwater on Mars, because water cannot exist in the liquid phase today on the surface of Mars because of the low pressure and the low temperature, but groundwater will be the remnant evidence of the similar climatic uh, of the factors between Earth and Mars. So if we find groundwater on Mars, we are not going to drink it, we are not going to colonize Mars, we are going to understand the similarities between Earth and Mars and understand if Earth, when and how Earth is going to finish like a desert like Mars. Okay? So how this radar works is very simple. You send a radio wave, and the first echo, it comes from the surface. The second echo comes from the aquifers. And basically, the electrical and magnetic properties of the surface of Mars define the penetration and the detectability of the groundwater. So we also use a technique called the time decay, which is basically the echo from the surface to understand the different composition of materials that are on Mars. And for instance, we would like to know if these basins and the plates, these rafted plates we see on Mars, are they made by volcanic or made by ice melting? And we come to find that these rafted plates on Mars are the remnant of a low viscosity volcanic flows on Mars, and they are not the remnant of ice. Another paper we had, which was on the first page of Science magazine in 2008, where we probed the polar layer deposit on Mars using radar, the Sharad radar. And basically, you can see that we were able to provide a cross section of the polar layer deposit on Mars and map the base of this polar layer, few kilometers deep. And something so impressive that you see that the polar layer deposits on Mars are layered, which means they formed over billions of years. And that means that water must have stayed long enough on Mars to form these polar layer deposits. If water stayed long, that means that we potentially could have some type of life developing on Mars. And based on these results, many In-situ rovers were developed to look for these evidence of organic materials on Mars, including the Curiosity rover, which is now looking for organics on the surface of Mars, and the ExoMars rover, which will be also looking for these in the upcoming years. But first, if we want to understand how groundwater evolved on Mars, one of the good places we look is, in fact, the Sahara. The Arabian Peninsula have many features that are very similar to the groundwater dynamic we see on Mars. For instance, like these big sinkholes we see in Qatar, and if you look at them, you will see that there are drainage which come up from the rim of the crater feature we see here, and basically, if you look at these, we find the same tapping feature we see on Mars. You see the tapping feature where water is flowing from the rims of the impacts we see on Mars. So when we studied these rims 2 years ago, we published a paper in Nature Geoscience, and we attributed all these flow features you see on Mars, which people they thought that they are the melting of the ice. They are not melting of ice. These are sapping feature, which means that when you have an impact on Mars, it fractures the ground, and these fractures of the ground, they reach the aquifers deep inside of Mars, and then water will sap up through these fractures and will create these features. So these linear feature, which are sapping feature, imply that there are groundwater on Mars. So this paper in Nature Geoscience, actually, when we published it, and we did explicitly compare these sapping feature to the ones we see in the Sahara, was the second must-read paper in Nature Geoscience. It was basically on every news outlet. And why? Because we show that there are groundwater on Mars with enough pressure to sap feature to the surface today. So this is now how you take the boring groundwater in our deserts and you turn into a key feature that explains to you that yes, by comparison, this tells us that groundwater on Mars today is still active. Another body which we study its interior feature and volatile, which means ice on it, is the Rosetta mission, which in 2014 we sent a little spacecraft to land on a comet 67P and to probe the inner feature. So why going to a comet has any implication to understand water on Earth? Because 20% of the water of our planet has brought to us by impact of these comets are very rich in volatile and organic material. And so understanding these comets is understanding the 20% of the water budget of Earth and organics on Earth and potentially the life on Earth. So Rosetta mission is one of the biggest and the largest missions. The solar panels are 50 meters because you are so far away in the solar system. So you need to have big solar panels to operate the spacecraft. And this is the lander, the Philae lander for both the Rosetta mission, and I was working on this Philae lander and the main spacecraft. So as you know, maybe potentially for those of you who follow the news of the spacecraft, when we landed on 2014, we lost the Philae, the lander, and then we started the rescue operation 720 million kilometers away from the Earth to retrieve that lander. And using the radar measurements, we were able to locate the lander on one side of the limb of the comet. And this rescue operation was published in Science magazine also. We were able to locate the lander and understand the inner structure of the comet. And the lander was found in 2016 during the last days of the operation. It was found, it was flipped in this shadowed area on the surface of the comet here. Okay, so if you are in Germany and if you go to Berlin Museum of Natural Science, you will find a display about the scientists who changed the vision of water, how comets brought life on Earth. And then you will find Messier, Galileo, and other old scientists, and you will find the new generation of scientists who work on comets and asteroids. And I'm super happy that my picture is here among many people of the Rosetta mission. I was born in an oasis in the south of Libya, and to be honestly, the first time I've seen water in my life was in a well in a desert, and I'm so happy to be one day participate in a team to look for water outside on the edges of our solar system of the Earth. So this is the Rosetta, the team who made the landing. And the two of these teams are, of course, from USC, my university where I work. And this is also making me super happy because one student we have landed on the moon and the two alumni of USC landed on a comet. So beyond the comets, we studied water on asteroids. So Vesta and Ceres are the largest two asteroids in our solar system. This is their size compared to the moon. And basically, Vesta is a very small, big rock, and Ceres is a protoplanet. And so my next mission was to look for ice and water on Ceres and Vesta. And why it's super important to do that. So we are not going to colonize here on Vesta, as you hear in the speech of Elon Musk, but imagine if these bodies which collide with each other, if they have ice on them, if they have water on them, it means that they can transport organics and potentially life across the solar system. And if a body like Ceres hit the moon, it can bring so much ice to the moon that maybe can make the moon habitable environment. So we used the bistatic radar experiment on board the Dawn mission, and basically we used the reflection of the radar on the surface of Dawn to try to look for evidence of ice on the surface of Hesta. And in 2017, we published in Nature Communication the distribution of ice on the surface of Vesta, and we came to suggest that Vesta not only have ice, but could have massive amount of ice on the surface of the Vesta. And the paper was written also in Nature by the editor of Nature, which was selected among its the editor highlight of one of the most important papers to talk about water in our solar system. So what we do with all of this is that we train the next generation of astronauts to go on these bodies and look for water, look for ice, to understand, maybe to stay longer on these planets, and use them as a base to go to Mars. And this is what's so exciting for me as somebody, again, who was born in the desert, and my biggest dream was, my dreams in life were super small. And so to find myself one day to participate in the astronaut training, real astronauts, that was amazing. And more amazing that to design the next generation of radar instruments that will support the astronauts looking for ice on the subsurface on the moon. And this radar probe the subsurface and display the result for volatiles and ice for the astronauts here. And so these are the NASA modules that will support the instruments when they will go back into the 2025 return to the moon. And these are the light modules, so when the astronauts can sleep in them. And then while they are in rest, these modules will be moving and will take them to the next location where they're going to explore. And these small rovers will support, so this is the prototype, will support identifying what will be the next location for them to be in. And these, of course, the images of the real astronauts using the radar devices to look for ice in the subsurface. And this is when they locate these in the subsurface, and the tested here are in the most deserts in the state of Washington. So something so amazing that in my life I have a dual life. My life of a scientist looking for water in the solar system, and this life was so glorious and happy, learned a lot. We got a lot of attention from the public and the media. And the other life is looking for water in the desert. I mean, this is where I go, where I came from. And so, unlike finding water on planet was so glorious and easy and funded and make you a happy person and pay you a big salary, finding the same water in desert is super challenging, because finding water in our area is not easy. And so why we have a problem? First, you have to understand that water scarcity in our desert area, it's not happened by surprise. It's a collection of ignoring the environmental and the climatic and demographic and operational constraints for decades. I mean, the biggest problem of finding water in the desert, that people think that this is not a problem. It's easy. There are mistakes at every level due to the lack of realistic and comprehensive long-term plan. So decision makers tend to think that water is free, water is given by nature, and so we don't need to do anything to find it or to preserve it. Also, there is no official program for water efficiency. We are talking all the time about producing more water, but we don't talk about being efficient using water. Subsidized water, free water, all of that shows that there is no market-based incentive to conserve water. Water scientists and engineers, which are supposed to be the hero, keeping the nation, the dry nation, hydrated, are actually underfunded, and one by one, they are escaping desert areas. Professionals in water science do not make the decisions, but basically decision maker will make the water science, make the policies in water, and which is also a big limitation of water science. And then the culture of respecting and preserving water is not there. So this is one to show you what is the future of our groundwater in desert area. So a couple of years ago, we published a model that showed the depletion of the major aquifer system for the next 35 years. So we reached that by 2070 years, most of the aquifers in the Arabian Peninsula, the shallow one, will be depleted. In 150 years, the major aquifer system in the Sahara will be depleted. And this is a big problem because this means that these aquifers which they serve today as the mitigation for drought will disappear, which means that we may not be able to mitigate drought in the upcoming 100 years. And if you're not able to mitigate drought and climatic fluctuations in these aquifers, you are basically going with a lot of socioeconomic instability in this area. So among of these areas, so we have Egypt and Libya are the nations who are going to have the biggest deficit under the different climatic models. So in this figure, you can see that the deficit 2016 and 2050, you can see that three nations have the problem: Yemen, Egypt, and Libya. Why? Because these countries, the deficit will increase, so Yemen is not so much, but the GDP is so low that this will impact food prices in a very drastic way. So Egypt, the deficit will increase the double. Libya will not double, but the GDP is low, which make Yemen, Egypt, and Libya completely unstable because food prices will going to be high as a function of this deficit rising up. So Egypt in particular is a very important case. It's a nation that didn't used to be in a water budget deficit. It now become a deficit. Since 2000, the water share per capita went from 1,000 cubic meter to today about 500 cubic meters. So Egypt is a nation that didn't have a water poverty issue. Now it's having a water poverty issue due to the increase in its population. And it have a deficit that reach about 20 billion cubic meter. So this is really a big deficit, which represents about 30% of the water share of the nation. So why this is a problem? So Egypt relies completely on the Nile as its primary source of water. But the Nile goes through other nations, but unlike many other rivers, the Nile the water coming to the Nile come from nine basins. Each of these have a very complex hydrological setup. But the Nile, unlike any river, it crosses about 4 to 5 climatic regions. So from wet to semi-arid, to arid, to hyper-arid, to Mediterranean climate. So all the climatic fluctuations in this basin impact the amount of water that goes downstream in Egypt. Now imagine you have a nation that for good number of decades has abundant amount of water, but due to population increase and climatic fluctuation, it is missing a lot of water, and it's becoming the largest water deficit we know for a nation today. And the increasing upstream damming here in the Nile in general make the Nile one of the biggest focus of water crisis on our planet. And this is particularly is not, as people can say in the media, this deficit is not due to the fact that upstream the damming is an evil thing, and damming is very important to regulate flow. But the problem is not in the nations upstream or downstream not communicating or not reaching an agreement about dams. The real problem is the unpredictability of the Nile. How can you make water share for such an unpredictable river? And you can see here the fluctuations in the Nile flow over 100 years. The Nile is very unpredictable. So making shares and making agreement of unpredictable river, it's really complicated, and I don't want to go in a lot of detail, but basically that is the major issue between Egypt, Sudan, and Ethiopia. So potentially, as we don't have so much time, I invite you to read our recent publication in environmental research letter, where we talk about the deficit downstream in Egypt, which is caused by the damming upstream, and how the damming upstream can increase the 21 billion cubic meter deficit in Egypt during the filling by about 9 billion cubic meter, and how we can mitigate that by longer filling periods, and basically by reaching an agreement in the filling and operation of upstream damming. And we propose the solutions for that, which basically the changes in the operation of the Aswan High Dam, and the use of the groundwater, and change in the vegetation, in the crop we are having right now, and modernizing the irrigation system. And this is basically the future work we are doing right now, in the future publication we are doing on this solution. And this is basically my life from Mars, asteroids, and comet, and the icy moons of Jupiter to the Nile River where I grow up. And I'm very happy to take your question. Thank you very much.
Dr. Essam, thank you very much for the presentation. Actually, I have two questions for you.
Mm-hmm.
I know that your major is trying to find water.
Mm-hmm.
What about mining and hydrocarbon in the solar system?
Okay, that's a very good question. So again, we go to the other planets because we want to explore their similarity to the Earth, and this is help us protect our own planet. So that's the primary goal of going to planet. Now, mining other planets, we have to think about the cost and the technology to transport anything from other planets. So for instance, sample return from Mars, bringing samples in this size of my AirPods, okay, it's a program that costs a couple of billions of dollars to bring something in this size. Now, if I'm going to mine planets, how much it costs to bring this? And is that cost efficient? Today, this is not cost efficient. Today, this is technologically unfeasible. It remains a topic that we always like to talk about, because from the common sense perspective, it's something that is of interest. But from what is more imminent for today, is to save our planet from the changes that it is undergoing.
Okay, I thank you for the answer. I have a second question. I'm not sure if it is similar or maybe like close to the previous one. A student asking, how does space exploration affect on the market of energy?
On the market energy. So space exploration, tell us about the climate. So I want to tell you something, that space exploration shifted a lot in 2000. So one of the big thing you ask, why people like me doing better science, doing environmental science. In 2000, the Earth Science Program started to be half of the NASA program. So NASA and European Space Agency now going to planet has become about half, and exploring our own planet, which we realize it is changing so much that we don't recognize it anymore. And that's become half of our own planet. But today, what it's understanding how the Earth is evolving, put the policy for energy, for the energy market, especially in terms of some gases we should not produce, like the CFC. So put the policy for pollution. So definitely all these policies are derived from observation made by satellites, made by space exploration of the Earth.
A third question, are there similar structure formed by water motion in Mars similar to Earth?
Excuse me, I did not hear the question very well.
Are there similar structures formed by water? It seems like he's talking about rivers or things like that, lakes, similar between Mars and Earth?
Yes, we do have lakes, buried lakes were founded on Mars. We do have the basins, like the watersheds, very similar to what exists on Earth. So yes, Mars today look like the deserts on our planet. And that's what we are discovering more and more, that Mars is our sister planet, is the twin of the Earth. So if you can understand the genetic disease that goes back to the life and water to disappear on Mars, we can get a window to see the future of our own planet.
Dr. Essam, thank you very much. It was an amazing talk.
Thank you.
You answered all of the questions we have, and I believe Dr. Solomon wanna say something.
That was very interesting presentation. Thank you so much. I would suggest for our younger audience, they probably would not realize how difficult it is to publish in Nature. This is one of the, if it's not the most difficult journal to publish in, and this that has the highest impact factor if younger students would understand that. Nature and Science. I'm proud to see that you published in both journals. This is
Many thanks, Doctor.
Very good accomplishment. I really loved your talk, and thank you so much. That was really great talk.
Many thanks, and my message for the young generation that is here. So keep learning. I believe the scientists have two roles in life. The first one is to make the discovery and understand how our Earth changed. And the second one is to really make an impactful and change and to fight ignorance and the spread of misinformation on our planet. And our planet needs every hand. So please keep learning, and thank you very much for having me. Thank you.
Thanks.
So Dr. Essam, you know, we have like a 1 minute, something outside the topic. You are Egyptian, born in Libya, and you lived some time in Tunisia, right?
Yes.
Yeah.
Yes.
This is very interesting.
Yes, I grow up in many places, and I have to tell you something. I've been working in NASA for 20 years in different capacities, and this was the only job I applied for. And this was my only acceptance, and my dreams were so small. And I have never thought that one day I will be working in NASA. And today I'm super happy to be leading NASA mission for climate study in arid area. It's a $350 million mission to look for groundwater on Earth. It's a concept development yet. We hope we'll go to the next phases. But when I was 20 years old, all that I was hoping for is to get some classes in astronomy. And I never thought that one day I would be working in these places. So please keep dream, because the world doesn't change with skeptical people. The world that change with optimists. Be optimist, and you can make the change. Don't be skeptical, please.
Very inspiring. Thank you very much, Dr. Essam.
Many thanks.
And we'll be happy to have you again one day.
Anytime. Thank you. Yes.
Okay.
Bye-bye. Thank you very much, Doctor. Bye-bye.
Bye.